Hey everyone, welcome back. This will be part B of lecture 8, and in this one we're going to discuss, we're going to get into the hyperbolic functions. All right, so we just finished talking through a whole bunch of examples of inverse trig functions, and now we want to turn our attention to the topic of hyperbolic functions. So many people will have not even heard of hyperbolic functions. I'm going to go ahead and just define them quickly, and through the definition you'll kind of see what they're kind of all about. So this is the definition, right? Kind of a definition, a pretty loose definition. So we call, there's the hyperbolic sine function, and it's denoted as like a sine but with an h there, and then you have the argument x. The hyperbolic sine of x is defined to be e to the x minus e to the negative x divided by 2. Okay. Similarly, we've got a hyperbolic cosine. Okay, and that's going to be real similar. It's going to be e to the x plus e to the negative x over 2. Okay. And all of the other variations of the hyperbolic functions are going to be derived from these two. Okay, so these are sort of the two important, well, they're all important, but these are the two kind of like fundamental ones, kind of like with trig functions in general. So then you would be able to define the others based on this. So, for example, the hyperbolic tangent is equal to the hyperbolic sine over the hyperbolic cosine. Okay, similar to what you'd expect from your regular trigonometry. Right, and then your cosecant and secant. The cosecant is 1 over the sine. The secant is 1 over the hyperbolic cosine. Okay, and then the cotangent is 1 over the tangent, hyperbolic tangent. Okay, right, so these are all kind of, they kind of come from these, okay? Okay, now let's go ahead and let's just kind of visualize these first two, just kind of set it up a little bit so that people can kind of get some sense for what these things are. So geometrically, what are these? Okay, so let's start with the sine function. I'll try to draw decent pictures here. It's helpful if you can kind of see them. So we'll start with the sine, the hyperbolic sine over here. So we remember that the sinh of x is equal to e to the x minus e to the negative x over 2. And so if we kind of mark this off, this will be like our 1, negative 1, and we'll say 1, negative 1 there. Right? So if I were to plot e to the x over 2, kind of this first piece of it, then it would kind of, so if this is 1, it would cut through the 1/2 spot because it's 1/2. But it kind of looks like this, right? So this is like e to the x over 2. Right? Now if I were to do the same thing with the negative e to the x over 2, negative e to the negative x over 2, right, this other piece, then it would kind of do something really similar, but sort of the reverse, right? It would sort of come like this, and it would cut through there, and then it would drop down like that, right? That's not the perfect picture of it, but you get the idea. Okay, so that's that one. Okay, now what the hyperbolic sine does is it kind of hugs both of these curves, right? So it sort of comes down like this, and then it cuts through the origin, and then it follows that one, right? So the sinh here is this guy, right? So it sort of hugs each of these, kind of goes like that. Okay, and obviously it's going to decrease without bound. It's defined on all real numbers. And so you can see what this is going to do. Okay, so that's the hyperbolic sine. It's this kind of connecting function between e to the x and negative e to the negative x. Now, what about the cosine? Hyperbolic cosine. We'll try to do the same picture over here. Oh, I've already wrecked it. Let me just get a new sheet. So, if I draw my x-axis, my y-axis here, then so remember the cosh is e to the x plus e to the negative x over 2, right? And so I didn't do this explicitly in the previous one, but you can see that that's e to the x over 2 plus e to the negative x over 2. Okay, and so it kind of has this, it's like the sum of these two, right? So let's, just like before, let's draw these on here. We'll start with e to the x over 2, which is just like what we drew previously. It's going to come up, pass through 1/2, and kind of take off, right? So that's e to the x over 2. And then e to the negative x over 2 is going to do the reverse. It's going to come up from this side, cut through the same point, and then take off. So that's e to the negative x over 2. Okay. And so what does the hyperbolic cosine do? Well, it's the sum of these two, right? So it's going to hug these lines, and it's going to come down and kind of do this. Sort of like a bowl right in the middle of them. And so the cosh is this guy. Okay, so just like with the hyperbolic sine, the hyperbolic cosine, right? The hyperbolic sine sort of hug these two curves. Hyperbolic cosine kind of hugs those two curves. Okay, so these functions, they sort of represent the interplay of, basically three functions: e to the x over 2, e to the negative x over 2, and negative e to the negative x over 2. Right, so the various sums and differences you can acquire between these, that's what the hyperbolic functions are all about. And then, of course, the hyperbolic cosecant, the hyperbolic secant, they're going to be just the reciprocal functions, right? So I'll leave it to you to go and research that piece of it and to get some sense for what those look like and what they're all about. There's a lot of things that are really kind of interesting about these functions. So they have a bit of a connection with the trig functions. Obviously, we've already seen that. But like, if you look at like a circle, okay, a circle is going to have the equation x squared plus y squared equals 1. Now, contrast that with like a hyperbola, which is going to have the equation negative x squared plus y squared equals 1. Okay, and so the circle, if we kind of plot a circle, so this would be 1, this would be negative 1, right? So like a semicircle like this. Okay, we could integrate over this region, right? It would be the integral from negative 1 up to 1 of 1 minus x squared, take the square root of that, right? And so I won't do it here, but I'll just tell you that when you do that, you get 1/2 times x times the square root of 1 minus x squared, okay, plus the arc sine of x, right? So the inverse sign here is on this, right? Right, and so this is basically the form of the antiderivative of this 1 minus x squared square root, and you can see that it's got this arc sine in it. Now, similarly, over here in the hyperbola world, if I have negative 1, 1, and that's a 1 there, my hyperbola kind of comes down and touches down here like this. So if I were to integrate the area here underneath that, then that integral would be negative 1 to 1. Let me put a line here so I don't confuse anybody. And then the integral would be 1 plus x squared dx. Right? And then again, I'm not going to work it out here, but what you would find out is that this is equal to 1/2 times x times the square root of 1 plus x squared. So similar to what we have over here. And then this other piece would be hyperbolic sine. Oh, sorry, the inverse of the hyperbolic sine. Okay. Right, so these two area problems, though seemingly quite different, although the equations are similar, have almost near identical forms, except one is arcsine and one is hyperbolic sine. So just like the sine function is related to circular motion and triangles inside of circles, the hyperbolic sines are related to hyperbola. Okay, and so you can kind of see some of the similarities here. Another thing about these hyperbolic functions is that many of the trig identities that we've been taught over the years are going to have corresponding hyperbolic identities, right? So, for example, if I take the hyperbolic cosine of x squared plus the hyperbolic sine of x squared, so I add those two together, then I can just, by definition, I can see that this is, I'm going to flip the page. I got lines blocking my, so if I have the hyperbolic cosine of x squared plus the hyperbolic sine of x squared, right, then by definition, the cosine, hyperbolic cosine is e to the x plus e to the negative x over 2, and of course if I square it, it's squared. Right, and then if I add to that the hyperbolic sine, right, like so, then if I were to expand all of this, I get e to the 2x, and then this would be e to the, so this, if I FOIL out this numerator, I get e to the 2x, e to the negative 2x, and then in the middle I get plus e to the x times e to the negative x, plus e to the x times e to the negative x. So plus 1, so I get a plus 2 in the middle, right? And then plus e to the negative 2x, and then that's all over 4, right, like so. And then over here, if I do the same thing, then I get basically e to the 2x minus 2 plus e to the negative 2x, and then again that's all over 4. Right, and so, actually this is minus, apologies. That's supposed to be a minus in the middle. Okay, so then I would have e to the 2x minus e to the 2x, right, so those go away. And then I would have e to the negative 2x minus e to the negative 2x, and those would go away. And what am I left with? 2 minus negative 2, so I get a 4 on the top and a 4 on the bottom, right? And so I get a 1. And so this is similar to obviously to the Pythagorean identity from trigonometry. So the hyperbolic cosine minus the hyperbolic sine equals 1, right? So the familiar trig identity, similar to the Pythagorean identity in trigonometry. Okay, so this is just a little bit of background. So let's go ahead and talk derivatives and integrals here. Okay, and again, we're just touching on this. These are just things that can come up sometimes in various kinds of activities. So you will sometimes see these. They're pretty rare though. But let's just talk about the derivatives and integrals here of this guy. So we'll let u be a differentiable function of x. Okay, then what do we got? Well, the derivative of the hyperbolic sine is equal to the hyperbolic, so this would be a u, sorry about that, hyperbolic cosine of u times u prime. Okay, very much the same as with regular trig. And so then, of course, that's going to imply that the integral of cos u du is sinh. Okay. And similar down here for the derivative of cos. It's sinh u prime. And so the integral of hyperbolic sine of u is going to be hyperbolic cosine of u, otherwise known as the cosh of u plus c, cosh u plus c. And the same is true for the hyperbolic tangent. Well, not the same actually, but secant h, hyperbolic secant squared of u times u prime. And so that's going to naturally imply that the integral of the hyperbolic secant squared will be tangent, hyperbolic tangent plus c. Okay, so very much like an analog of what we see with the regular trig identities, or the regular trig derivatives and integration integrals, right? Particularly these two, right? Well, all three of them actually. Okay, so obviously we're not going to prove all of these, but just to give you a feel for it, how to prove these, let's prove the first one, that the derivative of hyperbolic sine of x is in fact hyperbolic cosine of x. And so to do this, we just need to remember what the hyperbolic sine is. It's, you know, just a function of, it's just a combination of exponential functions, right? So it's e to the x minus e to the negative x over 2. Can we differentiate this? For sure, right? We could kind of pull out the 1/2 and then we could break it up if we want. But recalling that e to the x derivative is just e to the x, we can see that this would be e to the x. And then here you do have to use the chain rule because it's a negative x up top. And so this actually turns out to be plus e to the negative x over 2. And that plus makes all the difference. And in particular makes this equal to hyperbolic cosine of x. All right, so that's that first one. And then the u is incidental, right? So you can just kind of plug the u in. Okay. Let's do one more proof just because. You know, I do want to make sure I spend a little bit of time on these. So the tangent, the hyperbolic tangent. Okay, if we want to differentiate this, well, we have to remember what the hyperbolic tangent is. It's the hyperbolic sine divided by the hyperbolic cosine. Sinh x over cosh x. Okay, kind of a little slang terminology there. And then we can use the quotient rule to differentiate this, right? So it'd be cosh x times ddx of sinh minus sinh ddx of cosh over cosh squared x, right? And we can run through this quickly, and we get cosh x. What's the derivative of hyperbolic sine? Well, we just said that that was hyperbolic cosine. And the derivative of the hyperbolic cosine is the hyperbolic sine. Okay. And then, of course, this is all cosh squared on the bottom. And we get hyperbolic cosine of x squared minus hyperbolic sine squared of x all over cosh squared x. And this top piece here, this is what we just talked about, right? So there was a it was a little premeditated, right? When I threw in that Pythagorean identity for the hyperbolic trig functions, it was because of this. And so this is 1 over cosh squared x, which is what? What is it? It is sinh squared x. Okay, and so that's what we saw earlier. sorry, that's not, it's SECH squared x, hyperbolic secant, not the hyperbolic sign. Okay. All right, so that's a couple proofs, and then you could go through the rest of them. And of course, the derivatives being what they are implies the antiderivative, that is the antiderivative, and that therefore the integral is kind of get the integral for free, don't you? Let's do a few examples really quickly. So let's differentiate hyperbolic sine of x squared minus 3. Right, so in this case, you'd want to use the chain rule, right? So you'd have to differentiate the outside, which is the hyperbolic sine function, and then you'd have to differentiate the inside, right? So you'd say this is hyperbolic cosine of x squared minus 3 times the derivative of x squared minus 3. And so you get cosh x squared minus 3 times 2x. All right, so 2x cosh x squared minus 3. And so it kind of gets you the whole thing there. How about the derivative of the natural log of cosh x? Well, again, chain rule. So the outside function is the natural log of u, and then u is cosh x. So this would be equal to 1 over cosh x times the derivative of cosh x. And so that is going to be sinh over cosh, otherwise known as the hyperbolic tangent. Okay, and so that's good, right? So those two nice examples of differentiation. Now let's see if we can do an integral that involves the hyperbolic functions. So let's say we want to integrate hyperbolic cosine of 2x times the hyperbolic sine squared of 2x. Right, so something like this looks pretty ugly. You wouldn't want to meet this integral in a dark alley. It looks a little ugly, but it's actually not nearly as bad as it looks, right? Because there's some nice things here. So if we let u equal sinh of 2x, then du we know is 2 times cosh of 2x, right? Okay, and so you can kind of see we have most of it. So sinh of 2x gets us this, would be u squared. And then we do have the cosh 2x dx, but we are missing the 2, so we can use our old trick, right? We can just use our old trick to multiply and divide by a half. Two cosh 2x dx, right? So kind of taking this part, putting it over here, putting the 2 on the front, and then we're dividing by 2 up front, so that's okay. And so here is basically a half times the integral of u squared, and then this whole thing is du, isn't it? Okay, and so that means it's 1/2, and then this would be u cubed over 3, u to the 3rd power over 3. And so we get 1/2. Well, let's just write it as 1/6, huh? Right? 2 times 3. And then the u cubed would be the hyperbolic sine cubed, hyperbolic sine of 2x cubed. So sinh cubed 2x plus c. There we go. Okay, so these functions are kind of weird, exotic somewhat, but they kind of follow the same integration techniques can be applied to them, right? We can still use u substitutions. We can do all of the algebraic tricks. It's totally possible if you wanted to, you could convert this to e to the x, if that's convenient, and integrate then, right? If it's, for example, if it's hyperbolic sine of x, you can write it as e to the x minus e to the negative x over 2 and integrate if you want to. So they may be kind of crazy functions, and they may be things you haven't seen in the past, but they're not something to be afraid of. We don't really use them too much. They don't come up too much, but I'm sure there are areas of application where hyperbolic functions are used all the time. I just don't happen to know what that is. But I'm going to leave it at that. So this will conclude this lecture. Now in the coming lectures, we're going to be kind of shifting gears, jumping into the second major section of the course. Although it's kind of a shorter section, it's sort of distinct, and that's going to be differential equations. So we'll have 3, maybe 4 sections on differential equations. Just kind of an intro, primer. As I said, differential equations will have their own entire course that you will come across later after you take Calculus 2 and maybe even Calculus 3. So that's it for this one. Yep, and we'll see you guys next time.